All right, welcome everyone to our last of 5 distinguished lectures this fall. These are all brought to you by our industrial affiliate companies, and we'd like to thank them for their support and putting this series together. The speaker today is an old friend, David Culler. David is chair of the computer science division at UC Berkeley right now and leading a project on energy infrastructure. And he tells me the first time ever that Berkeley's not doing a computer building project?
No,
no, maybe too much, but very different than their usual. Yeah. David and I interacted a lot 10 years ago when we started the first 2 Intel University labs at Berkeley and here in Seattle. And that was a great time. We spent a couple of years really helping those things get off the ground. And we're happy to be able to celebrate their 10th anniversary this January. So looking forward to that. But I'll let David tell you about his new project.
Great. Thanks, Gaetano. Yeah, I think that's a good place to start. We didn't know what that was either. And as we dig into the energy problem, there's a certain amount of that. And there's plenty of room down here in the front. I have to... the faculty's all scared enough to be in the back or something. So we're going to do something entirely different, I suppose, and talk a little bit about energy and more than power. Some of this was, for me, a transition back to the university from spending some time at a company of tackling those things that matter that you don't necessarily know how to build a company around. And when I talk about energy, I'm really talking about the whole environmental impact of its extraction, use, and disposal. And in some sense, we're living here with the end of the industrial age. And in some sense, this is about how do we begin to look for information age solutions to the industrial age problem, which, as I'm maybe know enough about energy to just begin to be dangerous. I mean, it's an amazing bargain if you think about your electric grid. I mean, imagine somebody came to you with this engineering problem, deliver this high quality, perishable commodity to millions of customers over thousands of miles, synchronized to milliseconds. Oh, and by the way, nobody will ever place an order or a forecast or give you a plan. And I forgot to tell you, there's no inventory anywhere in the supply chain. Obviously, you would say that is ill-formed. That's not something we can do. We couldn't. We kind of worked our way into it. We bit that off because cheap access to high-quality power was the enabler of the whole industrial revolution. And we grew into this, and now we have a system at this scale. So, the way we have achieved that to date, little Grid 101, is a family portfolio of generation resources, baseline, intermediate, peaker plants, and so forth, delivered through an amazing transmission infrastructure to a distribution to a bunch of oblivious loads. And that ability to be oblivious to energy consumption is really what allowed industrialization to take off. Of course, the reality is a little different as energy becomes more dear, both, especially if you include the acquisition, the environmental costs. In many ways, energy efficiency may be a greater threat to the grid because it's going to increase the peak to average ratio. It'll be far more bursty when we stop wasting it so much. And yes, there's limitations in the grid. There's bottlenecks, the things that the utilities will worry you about. And the real issue is we haven't begun to think about seriously increasing renewable resources. And the fundamental question here is what's the penetration of those? If you think about it, so non-dispatchable means I can't determine when it goes on and off. Solar, we will make hay when the sun shines, when the wind blows. Okay, so fundamentally, we've been able to essentially predict and match the load through managing this tier of portfolio of supplies. And essentially, so we're in a regime of load following supply. Okay, we now have a set of supplies that don't like to follow the load. So ultimately, you got to introduce a set of loads that follow the supply. That's the only way that that equation adds up again. And the only way that you can do that is if those loads begin to communicate and the supplies begin to communicate, and we really start to have a grid that operates not open loop, but as a system. And like any other system, you have to have observability close around it. So in some sense, that's the question that we began with in the locale project, is how, given that the internet exists, given that we have communication, we have many of the tools, how would we rethink aspects of the electrical infrastructure in particular? So, we're all born and raised on Moore's Law, and some of us Bell's Law, a completely new class of computer system every year, and this, 75% annualized growth rate. Well, new class moats, we're proud of that. There's plenty more room for that to go. We have to begin to think about a different kind of roadmap. And this was a big change for me. It's like Moore's Law, but put the log on the other axis, okay? And you're getting close, that things move at an entirely different pace. But I want to pull a couple so this is looking at energy consumption in the United States. It's another one of these per capita. Over the last 50, 60 years, so you got to get used to some of that. And what you can see here is it increasing steadily until, remember, 1970s when we had the oil crisis and all of that. We actually did change. The real unit here, so the units here are energy per GDP. What that really wants to be is energy versus quality of life, because those are the things that, it's really the relationship of those. So focusing on the productivity part of it is the right thing to do. In those early days, we were getting more efficient by about 0.5% per year. And what really happened since the mid-70s is that the energy per GDP has been dropping about 2% a year, right? Big number, right, comparatively. So for example, that little piece down there is how much we've made up with additional supply. What we have saved is those 70 quadrillion BTUs, big funny number. You can think of it as an exajoule. And really the roadmaps we got to begin to think about, the first one shows what AB 32, the law of the land in California, attempts to achieve, getting back to 1990 by 2030. But if you imagine a 50% below where we were, or 80%, what really are the pathways that are going to turn this thing around and start bringing it down? There's big changes we have to affect if we're going to make a change to those curves in a more significant way. And once you throw in China and India and the rest of it, this is not tomorrow's problem, it's today's problem. So just to expand that out a tiny bit, load following supply, that's the regime we've been in for the better part of 100 years. The earlier version I had of this was from 2001. Remember when California went, before we went bankrupt, we ran all out of energy. What this is showing is in those hot summer days, the 30-some gigawatts that the state uses hops up to about 60 gigawatts as a result of residential commercial air conditioning, okay? And so you say, gee, you've built an entire system around statistical multiplexing, and it all depends on the fact that there isn't correlated use. All you have to get is a teeny little bit of correlated use, and all of that whole set of assumptions begin to break down. And this translates into a very expensive set of assets that you use only for a couple of days a year. The utilities don't like that. So this is where demand response and critical peak pricing, it's the thing that all of the smart grid is to go after because it helps the utilities save some money. And it's important to reduce the embedded energy in those power plants that only run a couple of years. But here's some other pictures that might question whether the grid today works so well, because how would you ever bring IT? It's so flaky, and internet, the electric grid has to be there working out. So this is, most grids, you have not the retail price, that's what you see, but you look at wholesale prices, which are typically done on a day ahead, rolling 1 hour market, and then you have a spot market that's an hour ahead for 5-minute intervals. In Europe, they were very successful with their PV initiatives, incentives. All of Bavaria now are barns like this that have nothing under them because they have such an in-field tariff. What this is looking at is high and low spot pricing over several months. And it normally bounces around 90 euros, but sometimes it goes up to 500 euros, and sometimes it goes to minus 500 euros. That there are times out there in the grid where you're getting paid really big money just to take energy down. And the view from Siemens and the like was, oh my God, even just this tiny bit of renewable penetration is throwing all of this off to where we can't even keep up with it. Well, California doesn't have much renewable. This is the spot price market back in September when I put this together. And of course, you can imagine I've grown up in this world of sensor networks and whatnot. We're busy just measuring everything and dumping it in a place that people can do it. And the California ISO, from my point of view, is just one more electric meter. What the hell? And so is its prices and the rest. So you see exactly the same picture, that as soon as you have, even without the penetration, a tiny misprediction between what you think the demand is and what it actually is, these huge fluctuations. Now imagine this is wind. There you see the fluctuations in the wind. This is coming out of a couple hundred megawatts of wind in Texas. There's the solar on my house, and you can see it on a nice clean day is the red curve. The blue curve, which is higher because it's a little cooler, you can see the clouds moving across it. There's my house. So much more variable source. So that's a little piece of what the problem is that we're beginning. There's a question of where do you start? Where do you begin as a computer scientist to even go play? And much like banks is where the money is, if you're worrying about electricity, you should start with buildings. So 3/4 of the electricity we spend in buildings. About half of the footprint. We expect it to double again in the next 20 years if left to its own devices. It's also where the worst kind of energy is spent, where most of the coal goes into electricity, except in California where we use gas. Oh man, a much better target for renewables than those cars and things like that. Buildings, they stay put, they're pretty stable, they're pretty predictable. So it's clearly the opportunity to utilize that. And of course, we have a whole... Buildings means homes, offices, everything that's structured. And the question is versus industrial. So there's a lot of industrial consumption that also happens in buildings. And so that, the various powers that be try to separate these. There's a different flow, the Sankey diagram to break it apart. The claim is that a lot of the industrial is separated out from this. I'm actually kind of amazed. Every year the DOE does these huge studies, and nobody checks the results of that. So, places in here for computer science to come to play, just actually making sense even out of the data that's collected on a national scale would be valuable. And, in each of these talks, you pick and choose the data that happens to make the case in some form. One there. Okay, so we got the electric grid. We have another international scale infrastructure, completely different set of design principles. And obviously, when we started in the project, a lot of this was the question of how could we take internet design principles and begin to apply them to the internet, to the electric grid? How could we bring them together? Think about the things that all of us in this room sort of take for granted. The notion not only of horizontal layering, but horizontal layering around a narrow waist, so that it's not just that somebody has confessed what each of the layers are, but that all of the top layers have to work with all of the bottom layers through this thing in the middle. Nothing in the utility space, the electric space, the building space looks that way. The smart grid, that would say it really should be a dumb grid with smart endpoints, because that's the only way that the infrastructure can evolve rapidly, is if you put the intelligence at the end. The notion that the internet's all best there. It's not very good, but we measure everywhere, we adapt. That's what TCP does. So fundamentally, that thinking about designing an infrastructure that's suboptimal at every point because it is better suited for change. There is nobody that is in the world of utilities or buildings that is thinking about that as a design principle, as a positive thing. That you want to have new technology roll in and everything above it should remain so that you can harness you're surprised that there's no innovation? You haven't designed for innovation. Why should there be? Much less that you should be able to roll applications into buildings. And the thing, of course, we take for granted, the internet was an overlay on the phone system, another one of these massive vertically integrated international infrastructures that we co-opted, and now we've reversed it. And in fact, that may be the most important thing, that it's very hard to begin to do any research in this area when you begin with, let me have a $100 million utility program. Whereas maybe, just like we're seeing innovation in the network, the notion that we can build overlays, a virtual private grid. Oh, and there's this other little thing about the web that maybe computers have to read these documents rather than people, and that there should be a simple form. So that's kind of what and where. How? So it's probably not a good idea to start all over with the new electric grid. Grid exists, internet exists. Pretty obvious approach is let's instead thinking about an intelligent energy network begins as an overlay on the two of those. One does the communication, the other one moves the electrons. That's pretty good. Put those two together, we can emulate most of what we'd like to achieve, and in fact, if we do it right, it probably should sink down. So then we can imagine, what would an energy subnet look like? What would be the equivalent of the router? What would be BGP? What would be the partitioning? What would be the transport layer? And we can begin to now start to build these things up rather than putting my combined heat and power in my basement and talking about power quality and the rest of that. We can imagine inventing concepts and embedding them and actually utilizing them, which means you can do really interesting experiments as well. I can use that wind farm in Texas up here. Who cares where the electrons come from? So in some sense, what we've been doing in Locale is to take that view that essentially think of this as a virtual private grid, just like you would your virtual private network. And it may even be the right thing to do. I mean, many of you probably pay, well, you probably don't, that little extra for the green power at the ski slope. It's the same electrons, it's the same ski lift, but you've bought your indulgences, you feel better. Well, you could actually do that if you had some of the same kind of technology that we have in the networking space. And so that if you really conditioned your load, we'll talk about that, you ought to see the benefits of it in your little portion of the larger grid. So how do we translate that into a project? Try to get some headway, actually progress in the life cycle of a grad student rather than in the next 50 years. So the way we have approached this in Locale was essentially to define 3 tiers of operation in the world we live in. So data centers, buildings, and connections out to a variety of supplies. The data center, of course, we're familiar with that because it's full of IT. It's also a systematically designed building for a purpose. We can measure productivity. It has something to do with how much work we get done. So you can imagine that there would be the machine room energy network, and you can already start to see some of the techniques. Obviously, we already have UPSs. Well, a little more intelligence, that could be an intelligent power switch. So the concept we're moving to here is wherever I move power, it used to be electrons were cheap and bits were expensive. Now it's kind of the other. So, move some bits with those electrons. So we could imagine some kind of a device that connected our computing resources to that energy network. Immediately you can start to see, oh, great, we should build power proportional schedulers for those and service managers. And we've done service adaptation for bandwidth, right? We could do that for energy as well. We can bring all of those techniques forward to where at least the IT side of the equation could be intelligent. Then you might ask, how would you represent that in aggregate to the rest of the energy consumption of the building? The HVAC systems, the office supplies, and so forth. How would they talk to one another? How would you represent the building to the rest of the participants? But you notice we're already getting the kind of hierarchy that we apply in tackling a lot of the other problems. And obviously, we should have those communication endpoints at the supplies. And then you might imagine a world where, for example, the building would put forward an aggregate forecast going on in time of its consumption. And the supplies would say, well, if that's what you're going to use, well, this would be my contractual obligation, and here perhaps what price might look like. And then perhaps you're actually tracked to that so that you have to actually fulfill that contract and consume that in some, or move things around or resell it and so forth. So what would be the set of protocols and whatnot that would put this in place? What would be the building blocks? So you can imagine we've called it here an intelligent power switch as kind of a conceptual building block, much like a router that would allow us to build bigger energy networks out of energy networks that exist, or littler energy networks out of ones that exist, much like we do in the IT domain. What would be the interfaces? What would be the connector? How do you scale up? How do you scale down? So those are the kind of questions that are driving the project. Where does it go? How much of that is wasted? How much of the rest can be optimized? In every other scheduling problem, we have a notion of slack. I have to get these things done. I have a certain deadline. I have some resource that I move around. In the energy world, since it's all as if everything were critical, and now I don't even have the equivalent of background versus foreground or interactive versus batch. So how much is there? How much? Now, all of these problems would go away if only there was the equivalent of a buffer. Right? So much of the design of the internet, at least, retry, building a reliable system out of unreliable parts, fine, as long as you can retry. How do you get some of that? Well, it remains a really important technological question to create energy storage. In the meantime, how do we emulate that out of all of the other forms we have? What are the fundamental limits? What are the protocols? You can see where this is going. Okay, so that's the big picture. What I wanted to do with the remainder of this is to kind of fill it in with bits and pieces of detail, and the Berkeley philosophy is eat your own dog food. So that's what we've been doing, and we've been digging around inside of buildings and measuring stuff. And so the remainder, I'm just going to kind of wash through a bunch of these activities to give you a little bit of a sense and the connection between what we do in computer system design and what we might do in these other domains for energy efficient buildings, for the grid, and so forth. So for starters, this is our buildings on campus. Kind of interesting. So this is energy density, kilowatt hours per square foot versus total consumption. The national average is about 15. That's the vertical line there. In fact, 80-20 rule applies here too. 10% of the buildings consume 75% of the power. They're 2 to 4 times the national average. There is Soda Hall, computer science right there in the middle. The physics is up there, who knows? So, and you asked, a portion of this is environmental, indoor climate conditioning. Part of why campuses are interesting is they're sort of microcosms of these larger problems. And if you think about it, we have kind of the operational load of Silicon Valley data centers in soda, semiconductor manufacturing. The life science up there in Stanley Hall is biotech. Koshland, actually, its electron microscopes seem to be the victim, which are on day in and day night. So here's what Soda Hall looked like a year ago. Nice, steady, 500 kilowatt load. Half a megawatt. 500 houses worth. Day in and day out, when nobody's there, in the middle of winter and everything. Yay. So you say, great, how could we possibly use all that? And you can go do your inventory and break it down, and lighting has a constant piece and a variable piece, and there's your HVAC part of it, and sure enough, we've got about 1,000 or so desktop and laptops, and that shows up as plug load mostly in IT, and we have about 1,500 servers and their PDUs and whatnot, so about half of that, 60%, is IT. How about that? That mix. Well, even breaking it down, that's a start. And yes, if what you took out of this was I'm going to go help on the portion of the energy spend that's IT, that's great. That's about 3%. And it's growing rapidly, and absolutely anything we can do there to lead rather than follow, and what you'll see is we're as bad as all the rest. Okay? Or if you get your inspiration there and you apply it to the other 97%, that's good too. There's a piece here that I think transcends the whole question of IT and the larger one, which is really about what it means to be an engineer. And it's a place where those other domains, mechanical and physical, pay attention to the engineering process more than we do, well, maybe with some of the old capacity planning. So think about engineering 101. You design the system, you plan it, you size it, you test it against full load. That's what we do every time we do performance analysis of our computer systems. How does it behave when it's running all out? We don't say, how does it behave when it's doing nothing? Right? That's where we measure it. That's what we do our safety analysis against. And then we add in some headroom for safety. We're good designers. You never operate any system at red line. But then we operate it at partial load. And this is where we stop. And the key is, for energy efficiency, this is the beginning, because all of it is about how well do you scale down from the design point at full load that you designed for to the operating point in reality at partial load. Okay, so we've all seen the Google paper. Even when you have millions of users and thousands of machines, you're on average 25% utilized, which means you're wasting 75% of your power because the individual building blocks of computers are so incredibly non-power proportional. So even Google is mostly idle. The machines in this building are maybe 2% utilized, if you're lucky. Okay, so let's think about that just a second. And this was the biggest lesson I learned from all of my low-power wireless sensor net. It's all do nothing well. It's great to do something a little better, but what really matters is doing nothing well. So I want to show you that if you had a system that was power proportional, then whatever it did when it was fully utilized, when it was 0% utilized, it used nothing. Okay? And at that point, okay, so we're looking at productivity versus consumption, energy versus GDP. That if I were 25% utilized and I did nothing, well, that's great. I'm 100% efficient. I'm using 25% of the peak power at that point. But if I'm spending even just 20% of my peak power when I'm doing nothing, then at that same 25% point, I'm only 60% utilized. And of course, as that standby power increases, the efficiency at the actual operating point just drops down. Okay? So the real issue is about not just measuring how well we perform, but how well we scale down, how well we do nothing. So here's the picture for your computers. It's very hard to find a machine. It has to be a real Mongo power hog like this one. Here's the latest barn burner out of Intel, where it only spends 50% of its peak power when it's doing absolutely nothing. And all that little stuff at the top you see, then the blue one, this one is all of your fancy CPU scaling and variable frequency. Here, the Atom processor, really great. It only burns 3 watts instead of 100, but you spend 24 watts doing nothing, right? This is the latest next gen, right? So it ain't, the CPU is the only part of the whole computer system that does nothing even remotely well. So to first order, if you just view computers as being on all the time like a light bulb, no matter what they're doing, that's a better approximation than any of the fancy power models that you'll see in the literature. This is in reality total systems, Dell, Sun. The blue is total consumption at idle. The little purple bar is how much more if you bothered to use it and you actually peg it. So as IT, we don't bring a lot to the party here so far, at least we haven't. So just getting our house in order would be useful. So you might ask, how power proportional are the buildings? So this is Corey Hall. Those guys over in EE, we're one department, so we're all. So they're a megawatt light bulb, and it goes from historically, and this has been true for 20 years, pick up another 200 kilowatts of load. So they're 82% or only 18% power proportional. Our friends out there in the biosciences, somehow they manage to spend 1.5 megawatts doing nothing, but they spend 2 when they do something, so they're 72%. Our friends in this is geology and whatnot, oh my God, they can spend 3/4 of a megawatt doing nothing and a megawatt doing something, okay? So this, if you were to run around with a unit and measure it everywhere, never mind all the detailed fine grain, no. How well do you do nothing? That metric by alone will give you most of what the fruitful results are in energy efficiency.
So how do you define nothing for really this stuff runs and
It's true. So that's the question is and of course what you'll find is when you go look at that stuff, you say, why is that running? So you can look at it over the entire year. You can look at it as your shutdown. And what it really does is it focuses you on the portion that is energy spend that nobody profits on. all of those lights in rooms that nobody's in, all of the conditioning of the environment where nobody is. I used to do a version of this where I had audience participation, because we measure everything. We built these little wireless power meters, and we built networks of those, and had refrigerators and all the rest. The one I liked best was my laptop connected to my display, and you could see that it did the right thing, it went quiet, and the display went down. And then I take my laptop and I unplug it, and the display comes back on to tell nobody that nothing is plugged in on the video cable anymore, all night long. Okay, that was the single biggest consumption in the whole laboratory. So this notion of doing nothing incredibly poorly just everywhere. Your ovens, right? So that's why it's a useful tool. Actually, this was a breakdown of that for the RAD lab, of where we're measuring each of the individual appliances and whatnot and building up that aggregate to get that picture. Okay, so one of the things we did, given this notion, we got together with the California Energy Commission to try to build a test bed for this building to grid, grid to building interaction. And they said, oh, well, you know, let's do it in a little challenging building like Corey Hall, where the electrical engineering side of our department is. I mentioned, there's the load. Look, there's a lot of information in that signal, right? That's a week of Corey Hall. This thing is built before World War II. You know, we added another floor on it. I had no idea that things, so we spent time, so an incredibly complex load that's all kind of canceling out in the signal. How do you get enough information that you could begin to forecast what's happening, how to go back and forth and interact between the two? The thing that's really the takeaway, and I'm going to do a couple of pieces, the part that's most interesting is this isn't about collecting a piece of information, and it's not even modeling systems, it's really the interaction. So in particular, of course, I can go instrument the entire load tree. And I have different tools for doing it at different places. We can do that in a bunch of ways. But what's the drivers of that, a lot of them are this underlying collection of systems that really is the climate plant. But the reason I have that is to support the activities, both the environmental and the productive activities, and it's really the relationship of the three of these things that you're trying to capture. And that's the both information collection, analysis, modeling, and algorithm piece is that. Whereas what we tend to focus on is measuring all of the different points and the type or vibration and whatnot, but it's really closing those three perspectives that is the real challenge in here. So part of what came out of this whole project was there actually is a very natural kind of separation that one can really begin to develop a layered architecture around physical information, and it's not what exists in any of the silos that are out there. I'm going to toss that out as an example of that. This was a picture of the physical tier that we put into that, ending up being thousands of sensors. You would have thought, oh, well, you put these wireless meters everywhere. The answer was no, for a lot of interesting little reasons along the way, although doing something as simple as you have your Modbus RS-485 high-quality meter, and then you go to Ethernet on a VLAN. What? That those concepts are completely missing even in this world, and this is everything. What we tried to do with this was to get the total energy flux through the building, not just the electricity, but the steam, the solar, and all the rest of it. One of the lessons here is never let a crisis go unexploited. So this is a little picture. What was interesting here was this is the point where we actually installed our hundreds of meters. And that was this amazing part where the transformers in our campus, we have a 12 kilovolt distribution throughout the campus, and then we have sub-meters in the building. They put the transformers in before they put the skins on the building back in the 40s. They can never replace them. So they have to keep them going, and so the campus electrician had to change all the toxics out of our transformers. So the whole project ended up being aligned so that in the 3 or 4 hours when we shut down the entire building, we would go in there and lay in place a whole information architecture before they powered the building back up. But along the way, there was a fire in the micro lab. Oh my gosh, a chance to turn off all sorts of things that people said you couldn't possibly do. And all of this was the improvement as a result of the planning phase. And we were also doing a move, and we were doing, so you never can do a controlled experiment. But today, Corey Hall is sitting there running at about 650 kilowatts instead of a megawatt, and it hasn't happened for decades. Oh my gosh, you know, this stuff, this building, there's these weird conduits and cables, and if you were to just scratch that 60-year-old rubber, we probably would have to tear the building down. So, I mean, the kind of care and not to mention that it would also kill you, but little details. So all sorts of different physical layers that will be the reality in any real building. So the biggest thing to come out of this project, actually, in my mind, is this very simple notion that there is a natural narrow waist in here that you could build out. We call it the simple monitoring and application actuation protocol. How about that? It must be simple. It's got an S in it. All sorts of different kinds of information feeding in to support a variety of different applications. I'm going to spend just a little bit on it, not because it's rocket science, but because it's so obvious and it takes a lot of care to do it. But then, you know, you don't need stack feet of protocols to do it. So basic idea is, of course, every instrumentation point ought to be a resource in a namespace. And of course, you ought to have a resource-oriented architecture for discovering what does, in this case, I have a Visalia weather station sitting there that I ought to be able to engage to find out what data streams it has. The difference between sensors and meters is meters only make sense for flows where you can accumulate them, which is easy to do with electricity. It's not so clear it makes sense for wind, for example. And of course, you can just walk down that tree to find the different kinds of information. And so much of this is about metadata management. And then, of course, once you're there, you can extract readings, and of course, they should be time-stamped. And of course, you should have sequence numbers and whatnot. I mean, it's all pretty obvious. And of course, along the way, you should be able to get to all of the schemas that would give you all of the rest of the information if you care. Okay, so part of what was important here was to not do all sorts of things. So we need to do sensing, metering, and actuation, essentially identify the sense point in the channel. And part of that is almost all instruments have quite a number of different channels. Our electric meters have 50 or so different channels once you deal with true and apparent power and power quality and power factor and harmonics and all of the rest, and voltage, and of course, right. So really you have many channels associated with every sense point, map those to resources, and then you can just walk down that tree, and of course, the important one is wherever you need to, you can go get the rest of the schema to get additional information. And the answer was you do it all in JSON, because no human being wants to consume this. Programs want to consume it. And you can do the transcoding from all the different pieces. Oh, there is a little thing that would be nice if we had events, and HTTP doesn't do that. The obvious way to do that, of course, is to register that with the device, with the post, and then it essentially does the gets periodically with the rest. And there's some things that you want to do, like I want it every 60 seconds, but never less than 50 or more than 100 because I only want the changes. But so, you know, a lot of that's a pretty natural thing to do. So we've gone around smapping everything, literally. So this started with zillions of meters and whatnot in Corey Hall. There's the power meter for all of the state of California today. You know, we got up to about 31. We just went through smart meters, and so, of course, the students have run around, and so this is one individual grad student's house, and of course we have weather and price and almost everything else that you can imagine showing up in this. So there's no question that you can bring all of this together, and as a tool, I point this out in part because all of this data is data that you can go pull out and take apart and do interesting things with. So the other piece that's going on here is also this design pattern. So recently, all of the low-power wireless stuff within the IETF has gotten settled down, in part because we introduced an adaptation layer. How about that 6LoWPAN that allowed us to carry IP over frames that were too small for that? Well, part of what you can see here is that, of course, the internet is end-to-end, and of course, it's end-to-end through all of those proxies. And some pieces of those are, if you like to, I mean, yes, you can put IP and TCP all the way down to those little nodes, and we do when you can run HTTP over it, and you can transcode it to a compact binary form, or you can transcode it to XML on the other side. And for all of those devices that weren't network capable in the front place, of course you proxy them so they look like it. So that part of the architecture just has to be there no matter what. And kind of beyond that, everything else. So now everybody is building all sorts of interesting applications. One grad student went off and did Facebook for buildings, Placebook, if you will, or Spacebook. I'll show you stuff with, of course, I can walk in with my cell phone and I can pick up all of these different things. And of course, everybody is building backends and databases and repositories to do the distillers, and that's what should be done. So in some sense, that's the key here, is to get to an information base where distributed innovation can happen. So this was just a little bit of a taste of it. I guess we have, what, now almost 5,000 channels within this one building to take it apart of all sorts of different kinds of things and various black boxes. So this is now Corey Hall. That's the building as a whole. And what's amazing is nothing inside looks like that. So this building actually has not one, but 13 different independent HVAC systems, all slightly competing with one another. That's one. You can see the central air conditioning. You notice it's not very power proportional. That's actually a much better one over there doing some of the offices. There's the modern piece up there in the CAD center on the roof versus the lab down in the basement. Maybe the students are there 24 hours a day, but I doubt it. There's all of the servers. Boy, look at how nicely power proportional they are, burning 40 kilowatts all the time. That's the various pieces of the microfab lab, the underlying infrastructure, the tools versus the equipment, so you can begin to put all that together. Lighting, all of the different plug loads, the parking lot. It turns out the parking lot runs off the building, and strangely enough, it peaks at 4 in the morning. God forbid. So you can begin to take all of this stuff apart and make sense out of it. Oh, this is, I mentioned it was getting better. We were doing a monitor-based commissioning simultaneously, and this was this great example. We had solved this problem, and it's a nice, cool day, which requires both that you know what's going on and you can dig down to the particular. In this case, it's a chiller up there on the roof somewhere. What's it doing running full tilt, burning almost 10 kilowatts on a nice, cool day in Berkeley? And the answer was they put it on a schedule, they did all the right things, and somebody went up on the roof and they flipped it over to manual. You flip the switch, and now it looks like that from then on. This is true for all building conditioning efforts, that they work great for a little while and then they atrophy because nobody is there seeing what's going on in the pieces. Okay, so that architecture is kind of falling into place. And you can imagine a set of core services, storage I mentioned, you can imagine higher level applications. Another student really working on, gee, what is the file system for all this streaming data and relate these 3 different worlds? You can have the taxonomy for each one of them and then symlinks, or should we do this as a database? All of that can go forward. And all of our statistical machine learning guys here is looking at real versus reactive power, the non-intrusive load monitoring kind of techniques. And there's all sorts of structure in this data that looks at first glance like it was just noisy signals. Okay. Let's bring some of this back to the IT world, things that we work about. So I mentioned that many of the building blocks are not power proportional. So we'll go a little fast. How do we build power proportional systems out of non-power proportional building blocks? Okay, so this is an example where all of our clusters have a load balancing front end. Make that your intelligent power switch that's doing load distribution and scheduling, essentially turning off the machines you're not using. And of course, the challenge here is you got to continue to service the load. What was interesting here, all right, so the picture is that we're sitting there at that point, and I'm running the Wikipedia trace as a driver for this. I know what my load is now. I have a set of machines that are running. I have to have enough machines in spinning reserve to handle the burst that I'm just about to get. So I have some bound on what that derivative looks like. I can maintain a set of spinning reserve, just like we do with the supplies on the other side, so that as it's ramping up, by the time those come online, I have enough additional reserve, and I can track that on the 2 sides. Okay? And the picture, this is showing the green is my current capacity, the red is the additional reserve, and the squiggly at the top is the actual power consumption. So that really does just track the load that I deliver. And this is showing at the bottom, if I don't do any of that, then my efficiency is essentially 1 over the load, whereas in a power proportional system, it's constant. You could apply the same technique to buildings. In fact, if you look at any particular building, those cruddy window air conditioners they use in China end up being 2 to 4 times more efficient because people turn them off. So it's this classic trade-off between the centralized system with high thermodynamic efficiency that you run all the time, okay, versus, oh, here's one. In Soda Hall, we have this 200-ton chiller. Over there in Echeverry, they have a 50-ton chiller. Well, it turns out that this 50-ton chiller would be enough to run both buildings 10 months out of the year. And the other one is more than enough to run them in the 2 hot months. So if all you did was pool the 2 of those, right, and then between those, you have something that's getting much closer to power proportional design. Okay, so we were all focused to do all of this very sophisticated scheduling and whatnot. The first answer is waste not. Eliminate that first. Until you eliminate the waste, you actually don't have any load to modulate. You're just consuming it all the time. Then focus on power proportionality. Then you can talk about sculpting it, identifying the slack, using it, and potentially using it in a way that is a good citizen on the grid. So in the last few, let me run through some of those latter pieces of some of the pieces in there. So I mentioned we measure everything. Here is a classic thermostatically controlled load, your refrigerator, all of the stuff inside of it. Think of a single cooling cycle. It's cold. It warms up until it gets hot enough to kick in once it exceeds the guard band around the set point, and then it cools down and it repeats that. So if you think about it, I actually had some slack in my energy consumption, and as the temperature approaches that point, I've lost that slack. So I actually do have a commodity that I could begin to shift. Okay? So for example, another grad student experiment. This is temperature, power consumption. Let's take the supply from the wind farm. Normally, my slack would vary just with that cooling cycle. But if all we do is, for example, identify a threshold that is when it is that I have excessive renewable power, the green power apart from the brown power point, if all I do is, for example, adjust the guard band so that I'll allow it to get a little warmer and go a little cooler in the parts where I don't have renewable, that's already enough to shift the consumption significantly. And I can go further with those set of techniques to where what you see here, the gray part is what I consume out of the baseline portfolio, the green being the part from the renewal, and the red being that which I saved. I don't have to have very many devices. This is a neighborhood full of refrigerators before I've significantly shifted the demand into the renewable part of it. I can play exactly the same game now to build the rest of these. I can embellish my IPS, for example, give it some battery, and now I can choose. So the demo that I'm not going to do is the one that live will sit there and I can pick a maximum power consumption or any profile of consumption. When I exceed that, I got to do one of two things. Either I got to draw from some storage, or I've got to degrade quality somewhere. If I imagine I had background load, like the other half of my Hadoop with the front ground, then I can begin to shift that, or I can begin to shift the fidelity just like we do. So we have all of these techniques that we could use to have at least that 3% that is IT be conformed to availability. And then the question is, can we apply those everywhere else? Okay, so you could imagine that now you do have that feed of availability coming in, of forecasts going out. You could begin to have devices like this operating in concert with the grid. And the question is, how many other kinds of systems could we do in that same way? Here's the same picture for buildings. You can save 30% in a moderate climate like the one we're in just by allowing the guard band in buildings to swing by an extra degree, which, by the way, you don't notice. Okay, so we're sort of moving into a direction where you could imagine that for every physical building, there's kind of the cyber analog where we're building up all of this information. We've got an environment where we can begin to run the models, we can do the predictions, we can begin to operate in concert with those external forces. And of course, then the question is actually the people. So one of the things that I'm most excited about is I finally have the reader I always wanted. So I mentioned that we're measuring everything. We're also tagging everything. So, there's QR codes on the refrigerator, and there's QR codes on all of our meters and on the plugs, things that they plug them in, because the real cost is building up the metadata that is the relationship of all these things that you're using. And of course, we tag the room, and we tag the building, and so sure enough, you can walk in with your cell phone, we tag all of the other things that are in the building, these things are going everywhere. And the reason that we're doing that is because I finally have my portable reader, which is the camera. I mean, it's nice to take pictures, but it's really, so yes, I can walk up to the building and I can point my camera and I can find all sorts of information about it. And of course, all of those sensors are feeding that data and the metadata. And of course, I can use that device also to configure it. I can swipe the refrigerator, connects to this meter, which is in this plug, and you know where that plug is, so you can connect the rest of them. And of course, I can use it both for configuring and because I have acquisition. So of course, you have the app then that begins to do things like, this is the refrigerator. Here's a bunch of information. It's a Energy Star qualified low utility bill, yada, yada. And I have various services, and one of them would be to look at the energy consumption of the refrigerator. Well, I mean, that would be fine. There's the defrost cycle and the duty cycle, but what's really going on is I can begin, for example, the undergrad Jeff that did this, here is his energy consumption across the things that are dedicated to him and his fraction of the shared. And of course, you could put that together to begin to look at your overall energy bill, and we could begin. Okay, so that's what's happened as a result of kind of focused on it, and I've sort of tried to indicate that we smapify everything. I don't care which link it is. You get it up to IP, and if you can't, you proxy it, and then it is. You move it around, and then all of the different kinds of applications that are getting generated around it. So, gee, we got shared resources. What might be, for example, a convenient interface to those, and how would I modulate sharing and access? That kind of sounds like problems we've seen before. So we can begin to ask, what would be the operating system for the building, the operating system for the grid? Where is data management? Is it file? Is it? And this is going back to that same picture I showed you at the beginning to kind of tease apart. Obviously, we've seen the load balancing scheduler. We've seen power cluster manager. What are the algorithmic techniques that we'll use in each of the different pieces to stitch these things together? Okay, so do nothing well. If you can't do anything else, do nothing well. Part of that is size for peak, but really it's that we do design for peak and we operate at partial. Demand response needs to be a continuous process, not this thing that happens on the 2 hot days in the summer. And we did this on the networking side. The challenge for low power wireless was to maintain the assumption of being always on when in fact you're always off. That needs to translate over. We know pretty well how to do it for IT equipment. I think that is one piece. Right? Can we apply that to all these other regimes? What that means is that we begin to have a cooperative grid. So, of course, all of the demands should be continuously monitoring, modeling, and taking actions to mitigate. Instrumentation's a part of that. You use that first to get rid of the waste and then to schedule the rest. Begin to have a bidirectional communication with the supplies for forecasting, tracking, and marketing, availability, and pricing. We're back to the old millennium. Make hay when the sun shines, right? So let me stop there. Thanks.
All right, have time for a few questions before the reception in the atrium.
I did not understand in what sense the IPS is actually a switch as opposed to a communication column. Is it a software-controlled on-off switch or something more than that?
Well, I think of it as a switch much more in network switches, bridges, and routers, that you've got multiple flows of information and power. The most obvious one is where I have some storage, like my battery backup, and then it's a question of when do I charge that, when do I use it. The more interesting one, of course, is where I have a collection of consumers, and I may actually be effectively sharing energy amongst them. A lot of it comes down to where are your availability sources. So conceptually, you want to think of it as steering flows of energy and demand. possibly in either direction.
So I'm interested in how you actually saved the 400 megawatts. And, I can imagine that some of it was data modifying human behavior. Some of it was a set of big bottles. You look at it, you say, duh, and fix that. What's the distribution of low-hanging fruit?
Yeah.
Things like that.
So the vast majority of it was big things that people thought they needed but didn't. We've got a chiller on the roof. It's got a 50 horsepower setting and a 15 horsepower setting. It's been running at the 50 for 10 years because surely that would be enough. Well, the 15 would be enough too. Oh, no, it might not be. No, you can do the calculation. It would be enough. So at some point, right? So there were a bunch of those kind of things. There were a whole bunch where you really did have simultaneous heating and cooling going on, and you had to go sort through that and figure it out.
Data, there's lots of low-hanging fruit. Is sort of the message here. Is that right?
With the initiatives to stick with it, because in many cases there was an individual that would say, oh, no, we couldn't possibly do that. And you had to stay with it, have enough commitment, and maybe somebody with a little more authority to push it through.
Over time as well.
Well, so that's, and yeah, so you had to have some motivation.
Well, thank you very much, David.
Pleasure.